welcome back, Calculus students. We're going to move on here and look at one of the implications that comes from a function being continuous. A little theorem in here called the intermediate value theorem. As I mentioned in the previous video, a lot of our theorems and work that we do in calculus hinges upon our functions being continuous. And this is just kind of our first example of what we call an existence theorem and an intermediate value theorem. Pretty big one for us as we continue our work forward. Then we're going to kind of switch gears kind of partway through the video and finish up chapter 1. We're going to take a look at infinite limits. And so when we get there, we'll take a closer look at those. So let's start by talking about intermediate value theorem. And so for the intermediate value theorem, what happens is we have a function f, and it's going to be continuous on a closed interval. And so we say if f is a function that is continuous on the closed interval a to b, then let's see, and k is any number between f of a and f of b. All right. Then there must exist a c value between a and b such that f of c equals k. All right. So that is the intermediate value theorem. Basically, I'm going to draw it here. Get this out a little bit. So basically what we're saying is if you have a continuous function on a closed interval a to b, then pick any number, any y coordinate between f of a and f of b. There has to be an x value that we can plug into the function and get that value to take back out. So I'm going to draw one out here, and we'll take a look at the importance of the continuity here. So here's my axes. I'm going to start by drawing a continuous function, and we'll show that this has to be true. So my continuous function does something like this, does something like this, something like this. There we go. Nice and continuous. And let's just have this be a over here. So there's f of a, and let's have b over here. I'm going to extend that axis here a minute. So here's f of b, way up here. Make the axis a little longer. So pick any value between those 2 points, f of a and f of b, on the y-axis, and there has to be a value c in the interval a to b where we get that value. So I'm just going to draw a horizontal line here that we can move around, and you can see that I can move this up and down, and it might hit the graph in more than one place. Might only hit in one place. But no matter what, wherever I put this, as long as I stay between f of a and f of b, there's at least one value in the interval. In this case, if I just drop straight down from here, there's my c value. If I move the k line down, well, then there's a c value, or here's a c value, or here's a c value. And notice, no matter where I put that, the c value is always in between a and b. So that's the intermediate value theorem. We've actually used this before, way back in algebra 2, when we were trying to justify where we knew a zero of a polynomial was. As long as we showed that the polynomial was negative on one side of the interval and positive on the other side of the interval, we knew it had to cross the x-axis somewhere in between those 2 points, because you can't go from negative to positive without going from 0. We kind of glossed over the continuity bit before, but that's exactly why that worked, was because we knew polynomials, they're continuous happens if we draw a function that's not continuous? You know, what happens in that case? So I'm going to just erase, oops, I didn't erase that. I'm just going to draw a different function here that has a discontinuity to it, and we're going to see, you know, how does that impact our function here. So I guess I got to go through A and A. I got to go through B and F of B. So I'm going to just draw a function that that is not continuous. Okay. So there's my function. F of B and F of A are still the same. Okay. But now look, if I put that red line back on there and I try and draw the red line so that and move it around, here's a K value somewhere between F of A and F of B. Notice it's you know, if I'm in here, even here, right? You know, if even there I can maybe get a value over here for C, but it's not in between A and B. And in between A and B, gosh, you know, there's a whole bunch of space in here where the function doesn't even have a value. Yeah, so the whole thing falls apart when the intermediate value theorem, it falls apart if the function itself is not continuous. So that's an existence theorem. It guarantees the existence of C as long as the function value is, or the function itself is continuous. We have to have continuity for that to work. So continuous function, sure, pick any point on the y-axis between F of A and F of B, move that line to any value of K, and you can get a function to equal that somewhere in between A and B. So with the function that's not continuous, that's not going to work. And so that's what's called the intermediate value theorem. And it relies heavily on the continuity of the function. And so hopefully that makes some sense. You did see it before. We just, you know, back in algebra 2, we didn't want to overload you at all. Talk about continuity. Okay. The other half of today's stuff is dealing with discontinuity. So the intermediate value theorem would definitely not apply to these functions on any interval that included the infinite limit. But basically what we're saying here, guys, is this limit still does not exist, and I think that's really important to remember. That just because we're going to define the nature of the discontinuity does not mean that it suddenly exists. These limits still do not exist. Okay, really important to remember that. Just because we're going to name it doesn't suddenly mean the limit exists. Because what we're talking about now, guys, is we're talking about limits that just happen to be infinite. So, you know, like if I say like the limit as x approaches C of f of x is infinity. That does, x approaches C. That doesn't mean suddenly this limit exists. It's still unbounded behavior, okay? Unbounded. We're just saying, oh, look, as we approach C, this function goes off to positive infinity. Or we could be negative infinity, and would still be unbounded behavior. So these limits still don't exist. We're just going to be examining the graphs for what the limits look like. And I put AKA vertical asymptotes in here, but that's really what we're talking about, guys. We're talking about vertical asymptotes. All the techniques that you learned for finding vertical asymptotes previously, that's what we're going to be talking about. So when we did stuff like f of x is you know, x plus 1 over x squared minus 1. You know, we said, oh look, x cannot equal positive or negative 1, right? We noticed the two discontinuities in there. Okay. And then what we were doing earlier with our limit work was we were removing a discontinuity. You know, that's still what we're going to do. Okay. Oh, so the x plus 1 is eliminated, but the positive one is still a problem in the graph. It's still a discontinuity. It's not removable. And then find the limit as x approaches 1 from the left, let's say, well, what happens? You know, if you're approaching 1 from the left, so you're like at 0, you're -1. At 0.5, you know, you're at -2, you know, and so on and so forth. So that's going to go to negative infinity. That's all we're doing. We're just classifying the kind of infinity we get. You know, if we approach 1 from the right, what happens to that? Oh, okay. Well, if you're at 2, you get 1. If you're at 1.5, you get 2, and so on and so forth. So that one goes to positive. So for a limit, as I think that it's just nice to let the reader know, like, what kind of infinity are we dealing with here? Is it positive, base, or negative? There's a problem in here that describes vertical asymptote behavior. It's a problem like this on that theorem. It's on page 82. So if you want to see the definition of a vertical asymptote, that is in our theorem 1.14. And it just talks about how exactly what we're saying here, that if we have that non-resistive continuity, and x goes to a positive or negative infinity, then that's what we call a vertical asymptote. So I'm not going to belabor that point too much, because I feel like your algebra 2 skills are probably good enough that you can find vertical asymptotes without too much trouble. What I did want to look at was something else in here that's actually another theorem, and a little bit more interesting, is theorem 1.15. Because this theorem deals with two functions, and depending on how we combine the functions, you actually can get one particularly interesting result that we're going to use quite a bit later. So we're going to say let C and L be real numbers. Okay. Let F and G be functions. All right. Where the limit as x approaches c of f of x is one of our infinite limits, and the limit as x approaches c g of x is equal to L. Okay, makes sense? So we have two functions. As we approach c, one of them is unbounded. The other one has a limit. There are a couple of interesting cases here, and I'm going to go through the first two right here. One interesting outcome of this is that the limit as x approaches c of f plus g or minus of x is infinity. You know, obviously, if you take infinity and add something to it, it's still infinite. Okay? If you take infinity and subtract a number from it, it's still going to be infinite. And then 2, the limit as x approaches c, f of x times g of x.
Positive infinity. Oh. Positive infinity if L is positive, or negative infinity if L is negative. So, so when you multiply, obviously infinity times a scalar is still infinitely large. Okay, but the third one, and this is the one that I wanted to get to, the third ramification here is the limit as x approaches infinity, oh, darn it, not infinity, x is approaching c, of g of x over f of x. Okay. Now remember, as x approaches c, g is approaching a finite number, L, but f is going off to infinity. So what happens to a fraction if the denominator gets infinitely large? This limit will be 0. And we are going to make use of this particular outcome quite a bit later on. So there's going to be some limits and some other things that we're going to be doing. And one of the techniques that we're going to use for evaluating some of those limits is going to be using this idea right here, that if we're looking as a denominator gets infinitely large, then we can actually show that that limit is 0. And it all comes back to this result right here. So we might see something along the lines of this. Now this is the limit as x approaches 1 from the left. And I've got the function x squared plus 1 over the cotangent of pi times x. Okay, now let's think about that for a second. In the numerator, what do we have? If x is approaching 1, well, that's just 2, right? But in the denominator, what happens to cotangent as we approach 1? Okay, now let's remember, cotangent, I'll just say of x, is cosine x over sine of x. So the limit as x approaches 1 from the left of cosine x over sine of x. Oh, sorry, there's a pi in there for this one. Doop, doop. Well, that means the numerator is going to go to 1, the denominator is going to go to 0, which means this is going to approach an infinity. And so as we're approaching infinity, now we have a constant over infinity. So this limit goes to 0. And that's what I mean by this particular result of theorem 1.15 is going to be more useful than the other ones. Of course, you just get infinities. So those limits still fail to exist. But this one actually results in a limit that does exist. And that's why I think the third result or part of theorem 1.5 is the interesting part. Okay, so that's it. That's really it. Intermediate value theorem, our first existence theorem of the year, relies heavily on the continuity of the function. And then these infinite limits, these are functions that have discontinuities in them. So it's still a question of continuity. It's also a question of finding a limit. And remember, these limits still do not exist. I hate having to grade tests and mark stuff wrong when I say, you know, does this limit exist? And they say, yes, it does exist. It's just infinity. It's like, the limit still is unbounded. So it's one of the 3 conditions that doesn't exist. It just happens to be in this case, we describe the nature of that limit and the fact that it's unbounded. All right, guys, that's it. Page 85 and 77 today. For those of us that are working on this asynchronously, I hope that explains enough. And we'll be running back through this stuff next week on Monday. So, all right, thanks. See you later.